Hi everyone, I'm going to go over in this example how to check if it is a binomial setting. We're going to create a tree diagram, and from the tree diagram we're going to show all possible outcomes. So let's read the example. A basketball player can hit a three-point shot 40% of the time. Suppose that in a game she will get 3 chances to make a three-point shot and that all 3 shots are independent. Create a tree diagram that shows all the possible outcomes of the 3 shots. So first we're going to check if this is a binomial setting. So there are 4 things you should check for a binomial setting. Let's go ahead and pull out important information from this paragraph. First of all, it says she will make a shot 40% of the time. So this right here is the probability of success, and that is 0.4. That means that she will miss a shot 60% of the time. So I can already call Q for failure. I'm going to call that 0.6 for missing a shot. So this is making a shot 0.4 and missing a shot 0.6. All right, then it says that she will get 3 chances. That is our total sample size. In other words, we're going to have 3 shots. So our n is equal to 3. So let's go ahead and check if this is a binomial setting. So the first thing is if we have a situation where it is right or wrong, true or false, where there's only 2 possible outcomes. So in this case, she either makes a shot or she misses a shot. So we can say that this is 2 possible outcomes. So that is the first thing that we check. The second thing that we could check is that our sample size is fixed. In other words, we know that she's going to take 3 shots. So that means that is the second item. The next thing we want to check is that our probability doesn't change. So in this case, our probability is 40% of the time. So our probability is 0.4, and that will be the same every time she takes a shot. There's a 40% probability of making the shot. And the last thing we want to check is for independence. That means the first shot she makes will not affect the second shot she makes. So we say this is independent. Since all 4 items check, we could say that this is a binomial setting. Let's go ahead and create a tree diagram representing this problem. So I'm going to go ahead and I'm going to draw 0.4 for success, 0.6, what we have over here, is failure. That means she makes a shot, that's 0.4. She misses a shot, that is 0.6. So I'm going to go upwards for making a shot, that is 0.4, and 0.6 for missing a shot. So in other words, when she takes the first shot, she'll either make it or miss it. The second time she takes a shot, she could make it, that would be 0.4, or she could miss that shot, so that would be 0.6. But we're not done because we want to make 3 shots. So the third time she takes a shot, that could be a success, or she misses it, so that will be 0.6. So I'm stopping after 3 shots. So I could see right here, if I follow this branch, this represents making a shot 3 times in a row. In other words, 3 successes. All right, so far I have 0.4, 0.6. Let's go ahead and draw the diagram from here. So 0.4, first make a shot, 0.6, miss a shot, then going up, she could make the shot. That finishes that possibility. Following along, 0.4, 0.6, that's a second shot. Third shot, she will miss it. That is 0.6. All right, so I did all possible outcomes for making the first shot. What happens when you miss the first shot? Then there could be other possibilities, such as if she misses the first shot, she could take a second shot and she could make that shot, or she could miss the second shot. Now, pay attention to each time I create a branch, they are mutually exclusive. So for example, the first time she makes a shot, she could either make it or miss it. And if you see the 2 add up to 1 or 100%. The second shot, she either makes it or misses it. So those are mutually exclusive. She either makes it or misses it. That adds up to 100%. The third time she takes a shot, she either makes it or misses it. And likewise over here, she either makes it or misses it. So every time you are creating the branches, they are mutually exclusive when you add them up. In other words, they add up to 100%. All right, let's continue. What happens if she misses the shot? So she misses the first shot. If I follow this, that means she makes the second one, and this one will mean she makes the third one, or she could miss the third one. All right, going down here, 0.6 misses a shot. Second shot she misses. She could make the third shot, and she can miss the third shot. So it's either this direction or this direction. So here we have the set of all possible outcomes. And as I mentioned before, probabilities multiply each other. What would be the probability of making 3 shots in a row? That means 0.4 times 0.4 times 0.4. So I'm just going to write this as 0.4 cubed. And I'm going to multiply along all these branches. So the second possibility is that she makes the first 2 shots right here. She makes the first 2 shots, but she misses the third shot. So I'm going to go ahead and always write 0.4 first. This will be 0.4 squared because she makes 2 shots, but but she misses the third shot. So I'll write 0.6. And for now, I'm actually going to put a degree 1, because if you notice, at the end of each outcome, it is always to the degree 3. So this one is degree 3. If I go below, I have a degree 2 times a degree 1. That is a degree 3 as well. I'm going to go ahead and follow the next outcome. That would be 0.4 right here times 0.6 times 0.4. So that means I have 0.4 squared again, and I have 1.6. All right, following the next outcome, which would be right here, I have 0.4 times 0.6 times 0.6. So that is 0.4 to the first degree times 0.6 squared. So I am writing the 0.4 first just to keep it organized, and this is 0.6 squared. Looking at our outcomes on the bottom, I have 0.6. That means she misses the first shot, she makes the second shot, and she makes the third shot. So that would be 0.4 squared, and I'll put a degree 1 here to show you. So 0.4 squared times this 0.6. All right, looking at our next outcome, we have 0.6 times 0.4 times 0.6. So that means 0.4, there's one of those, and there are 2.6 here, 0.6 squared. That means she makes one shot and she misses 2 shots out of 3. All right, and then we have 0.6 times 0.6 times 0.4. So this outcome is 0.4 times 0.6 squared. And the last possibility is that she misses all 3 shots. So right here I have 0.6 times 0.6 times 0.6. So that is 0.6 cubed. The important thing with binomial setting is that how many ways could she make 3 shots? So if you look at the first outcome, there is only one way that you can make 3 shots in a row. So I'm going to go ahead and just put 1 here. If we look at making 2 shots and missing one, how many ways can this occur? So let's go ahead and count this. This is 0.4 squared times 0.6. There's another 0.4 squared times 0.6. And down here, there is a third 0.4 squared times 0.6. In other words, there are 3 ways we can make 2 shots and miss 1 shot. Likewise, if we look at missing 2 shots and making 1 shot, there are also 3 ways this could happen right here. Making 1 shot and missing 2 shots. So there are 3 ways that could happen. And lastly, there is only one way you can miss all 3 shots. So we're going to use this when we create our binomial model. We can see if x represents making a shot, right here we have let x equal the number of shots. So in how many ways can she miss all 3 shots? We saw right here from the tree diagram that there is only one way you can miss all 3. In other words, 0 shots, that means you miss all 3. So that would be one way, and I'll just put 1 even though we don't really need it there, times 0.6 cubed. And how many ways can she make 1 shot? In other words, she will make 1 shot and she will miss 2 shots. Well, looking at our probability model here, there are 3 ways she can make 1 shot and miss 2 shots. So there are 3 ways that she could make 1 shot and miss 2 shots. So I will just write 0.6 squared times 0.4. So this represents missing 2 shots, making 1 shot. In how many ways can you make 2 shots and miss 1 shot? So let's go ahead and let me highlight. This will be 1 way of making 0 shots, 3 ways making 1 shot, missing 2 shots, and there are 3 ways of making 2 shots. That means if you make 2 shots, you miss 1 shot. So I'm going to go ahead and write you miss 1 shot, so that's 0.6. 0.6 always represents missing a shot, and 0.4 always represents making a shot. Probabilities multiply each other. You're going to make 2 shots, you're going to miss 1 shot, and there's 3 ways that could happen. And lastly, if you look at the tree diagram here, there's only one way where you could make 3 shots. That means you're going to make the 3 shots for every time you shoot. So that will be one way of making all 3 shots. So 1 times 0.4 cubed. Now, if you remember from Pascal's triangle, what I showed you in class, we are actually, because our n equals 3, that means we are in the 3rd row of Pascal's triangle. I'm just going to recreate Pascal's triangle, just the first 3 rows. That means I start with a 1, I end with a 1. This will be the 2nd row. And if you look at the 3rd row, it is 1, 3, 3, 1. That corresponds to the outcomes, all possible outcomes for 3 shots. So 1, 3, 1. Now, to answer the question, it says, how many of your above outcomes end with making 0 shots, 1 shot, 2 shots, 3 shots? So here is the possibility of all outcomes. Now we can answer probability questions such as what is the probability of making 0 shots? In other words, when x equals 0. Well, then I would just look at my probability model, and the probability of making 0 shots would just be right here, 0.6 cubed. And then you can just calculate that, and 0.6 cubed is 0.216. And you can answer many probability questions. For example, what would be the probability of making more than 2 shots? Making more than 2 shots is equivalent to making 3 shots, because not including 2, more than 2, means the probability of x equals 3. If you look at our probability model, that would just be 0.4 cubed. Well, 0.4 cubed is 0.064. And there you go. Here's an example of a binomial setting with a tree diagram and a probability model.